Okay, so let's now look at another example for exponential growth and decay, and we call this example number 2. So now, this time, let's see, part A of the example, a given amount of carbon-14. Now, you don't have to be too concerned about what carbon-14 is, okay? It's just one of the most general type of carbon existing out there in nature. And carbon-14 here, I mean, it's a chemical substance, and so the expectation here is that over time, any chemical substance will break down itself and losing its own, amount. And so that's why in this problem here, it says a given amount of carbon-14 will have decayed to half the original amount. Now the key term here is half the original amount. So what are we expecting? We are expecting a half-life problem somehow, right? So, by the way, so it's decayed to half the original amount after 5,715 years. And then now find the function to model this exponential decay for carbon-14. Alright, so now, right now, in the way how it's laid out, right? I mean, once again, you can always pause the video to write down the questions yourself, okay? And I'm going to switch back to my document camera here. And so what I see here is that in the way how the problem is written, then the meaning of the 5,715 years right there, that is our half-life right there. Because that is, if you read again into the problem, 5,715 years is how long it takes, right? How much time it takes for a certain amount of carbon to lose and remain only half of it, half of the original amount. And so now I'm safely starting my problem with knowing that T1/2, which is a notation for half-life, right? T1/2 here is going to be 5,715, okay, years, and that's the units for time here. So now, what's so nice about knowing the half-life here? Because now, remember I gave you the formula earlier, T1/2, right, equals to natural log of 2 divided by K. Now, with this formula right here, it enables us to find the K, which is the decay constant, right? I mean the decay rate constant for the equation, for the function that we need later on. And because the question, once again, the question wants us to find a function to model the decay, the exponential decay. So we need to know the K right? We need to know the decay rate. And so now, I do know T1/2, right? My equation now become 5,715 equals natural log of 2 divided by K. And that is all because 5,715 right here, substitute for T1/2 in my equation. And so now to solve for K, this time here we don't even need any sort of, taking natural log of both sides or, this is not an exponential equation, it's just like a usual, the simplest equation as the way it looks. So K here, to solve for K is actually just simply, if you multiply them across it, straight across, and then you divide it down and you have ln of 2 divided by 5,715. Okay? Now, before I proceed any further, this is a friendly warning, okay, or a friendly advice here, okay, you can take. This sort of work right here, the formula for half-life here, I strongly recommend that to the people who are planning to take chemistry 2. Okay, general chemistry number 2, because you are going to do this a lot in your general chemistry number 2. So make sure you master with this. So it's not just in this math class that you are learning, but it's anywhere. Right? You can see it a lot. And so now K, this is the way how to find K. Right? So all I have to do is natural log of 2 divided by 5,715. So now in my calculations, then I will have, let's say, ln of 2, okay, it's 0.693. We can always do ln of 2 can always be used with an approximate 0.693 and divided by 5,715. Okay, so now my calculation is going to show 0.693 divided by 5,715. Okay? So the number here is 1.21, okay, times 10 to the minus 4. Now, I hope you are not surprised about this notation. This is called scientific notation. It just means it's actually, it just means that it's 0.0000121. Okay, but then instead of writing it as, with that much, leading zeros in front of the 121 like that, then we decide to write it. We decide to move the decimal point backward to the right here, 4 units. So that's why it's 1.21 times 10 to the minus 4, So either way is fine. If you want to use that way to express the number, that's fine. If you want to use the scientific notation, that's fine. Okay, so the idea now is k equals, that is k, right? So now our function here is going to be what? A equals to a sub 0, right, times e to the minus, because it's a decay problem, so the k has to have minus in front of that. Minus 0.000121 t. Okay, so that's the equation. And then so now in this problem in particular, you don't even need to find out, you don't even need to worry about the initial population here, because I mean we just know that at whatever time later on, right? At whatever time later on, the decay here is always going to be that much multiplied with the initial population. That's all we need. Okay, so that is the answer to our problem there. Okay, so now let's move on to part B of the example. Okay, so I'm going to switch back to my overhead projector screen right here. I mean my PowerPoint screen. So it's a story that the analysis indicated that the Dead Sea Scroll, it's some kind of antique stuff basically. I mean the Dead Sea Scroll wrappings contain 76% of their original carbon-14. Okay, and we want to estimate the age of the Dead Sea Scrolls. The point here is that pretty much any object in our living life right here contains carbon-14. That's the idea. Okay, and so we come up with a technique to measure the current amount of, we come up with some kind of technique to measure the current amount of carbon that exists in the objects on the present day, and then from there we can estimate like how much it is as a ratio compared to the original amount. And so basically, and that's the technique of what's so-called carbon dating. But so now what I see is that in this problem, what I understand is that the Dead Sea Scroll always contained carbon-14, right? Now compared to the original day, it was some full amount, 100% of carbon in there. But then at the time in this present year right here, it's only 76% left. That means it's only a portion of the original amount. Okay, so we need to find out how much time it took, right? We need to find out how much time it took to reach down to only 76% of the original. So take a moment to write down the problem, or you can always pause the video. But now I'm going to switch back to my document camera here. Okay, so the idea now, the equation is always the function that we know. We can make use of the function from part A that we derived, right? The equation from part A is A, which is the amount of carbon-14 at any time, equals to the initial amount of carbon-14 times e to the minus 0.000121 t. That is our equation for this problem. And then what do I know? I just know that I don't know how long it has taken that. Okay, I just don't know how long it has taken. But then all I know is that at this time, at the time that we found that Dead Sea Scroll, at the time we found the Dead Sea Scroll, we know that there's only 76% of the original carbon amount left over. So this is how we express the left side of the equation right here, 76% A sub 0. because once again, at the time when we found the Dead Sea Scroll, there is only a portion which is 76% of the original leftover. And so this is what we substitute for the left side, 76 over 100 of A times A sub 0 on the left side. And then that equals to A sub 0 times e to the minus 0.000121 t on the right side. Okay? And so now, at this point here, we have a common factor of A sub 0 on both sides. We can just simply divide both sides by A sub 0, cancel it out. Okay? So what I have left is a 76 over 100, right, equals e to the minus 0.000121 t. Okay? And then now this equation here, we want to find out time, how much time it takes to reach only a 76%, right, of what's original. And so now what I need to do is to solve for t. I have, my equation turns out to be 0.000121 t without the e, right, equals to a natural log of 76 over 100. All right? And then once again, furthermore, to compute t, all you have to do is divide both sides by minus 0.000121. Okay, divide both sides by that much amount, 121. Okay, and that's going to give me t equals, and then once again, we're going to go ahead and compute this amount right here. So now, I'm going to, according to my calculations, then let's say 76%, which is 76.76, and you're going to take natural log, okay, and then you're going to divide that by minus 0.000121, okay, and so the answer now is going to be a positive. The answer is supposed to be a positive. So 2268.07 years. All right, so now what is the meaning of this value that we have just come up with? This is the time it takes, okay? It's the time it takes, how many years it takes, right? To decay the original amount of carbon, right? To break down the original amount of carbon to only 76% remaining, okay? All right, so that is all with exponential growth and decay, right? And so you can always, pause the video or rewind and review the video anytime, and you can always have, the option to contact me and have questions or anything like that, okay? And I'll be more than glad to answer the question for you. All right.